Hello, and welcome to the video lecture for topic 19, electrophilic addition, or what I like to call backwards elimination. So, in topics 17 and 18, we saw two ways to perform an elimination, and the overall change in an E1 or E2 reaction is removing a leaving group and a hydrogen to create a new pi bond. What we're going to see in basically topics 19 through 23 is that we can do the reverse of this reaction, right? Except now we're going to add a nucleophile and an electrophile across a pi bond. So in elimination, we take two sigma bonds, get rid of them, form a new pi bond. In electrophilic addition, we're going to take a pi bond, get rid of that, and form two new sigma bonds. So our understanding of electrophilic addition is best examined by reviewing the last step of an E1 elimination. So if you recall, in an E1 elimination, we form a carbocation intermediate, and after that intermediate is formed, a base comes along to remove the beta hydrogen and create our alkene. So, and now here our hydrogen is bonded to our base. So we can consider this as an acid-base equilibrium. I have something accepting a proton, something donating a proton, right? And so that's the classic definition of a Bronsted-Lowry acid-base reaction. And so if we think of the reverse of this process, so here's our base, and here's our acid, we can think of the other side as this is now our conjugate acid, and the alkene is our conjugate base. So because we have the ability to, because we can see this relationship, we can now begin to think of pi bonds in terms of them being a weak base. And in fact, a pi bond is a very weak base. And so, right? And so from there, we just have to determine what the degree of this equilibrium will be. Well, I'm going to get rid of my arrows now, and let's just think of this in terms of pKa. We've seen before how we've talked about how this hydrogen, this beta hydrogen on our carbocation, has a pKa of approximately -9. So that means it's going to be a strong acid, which means that the conjugate base is going to be a weak base. Similarly, we've seen how, right, this base is going to end up becoming a weak acid. And so we can say that our equilibrium mostly lies on the side of our conjugate products, but that this reverse process, or what for electrophilic addition will actually end up being our forward process, is actually going to be occurring just enough that we can capture this carbocation with a nucleophile. So step one in really understanding these electrophilic addition reactions is we can think of our alkene as a weak base, and we can think of this acid species as something that is an electrophile bonded to a nucleophile. Now, that makes sense to a certain degree. This hydrogen in an acid, right, is going to be electron deficient. It is going to be seeking electrons. We can think of that as an electrophile. And this base molecule, right, it's going to, once the bond breaks, if we think of it over here, where it's got this lone pair now that can do a job, we can think of that as a nucleophile. And so we have this base, we have some sort of electrophile nucleophile combined into one molecule, and the first step of this is going to be, right, our alkene taking its the electrons in its pi bond, reaching out, making a bond to our electrophile. That's going to break our nucleophile off. We're going to form a carbocation. we've attached our electrophile. And then finally our nucleophile, with its newly formed lone pair, can come and make a bond. And we see how we have taken a pi bond and now created two new sigma bonds. So up here we have elimination, whereas down here below, this is electrophilic addition. Okay, so now I'd like to start getting into some of the specifics of this reaction, right? Things that we're going to need to be aware of, where things bond, how things behave, and then we're going to take a look at three reactions at the end of this video lecture to start off our study of electrophilic addition. Now we just saw how our alkenes can serve as a weak base. And so we're going to look at three reactions at the end of this video lecture, right, to start off electrophilic addition. But the first two of those reactions have some sort of an acidic proton involved in the species that's going to react with our alkene. And so I'm now going to draw an unsymmetrical alkene. So we'll have a couple of methyl groups on one side of our alkene, and we'll have, let's say, a methyl group and hydrogen on the other side of our alkene. Now I'm just going to pick a generic reagent that I'm going to call H nucleophile. And we know that the first step is going to be that our alkene is going to use its pi bonds to go ahead and grab that hydrogen off of our nucleophile. And the question we have to ask ourselves is, which of the alkene carbons is that hydrogen going to be bonded to? So our arrow pushing for that from the alkene to the hydrogen, and this bond breaks to give the electrons to the nucleophile. Now, we can have one of two results. And I'm going to call this carbon 1, and I'm going to call this carbon 2. If the hydrogen attaches to carbon 1, we form a carbocation that looks like this. If the hydrogen attaches to carbon 2, we'll form a carbocation that looks like this. Now, if we compare these two carbocations, we see that process 1 leaves us with a secondary carbocation, whereas process 2 leaves us with a tertiary carbocation. The tertiary carbocation, as we know, is more stable than a secondary carbocation. And so based off of that fact, it is process 2 that will occur, and not process 1. Now, we can summarize this by saying that in electrophilic addition, remember we said that that hydrogen can be considered an electrophile. We can summarize this by saying that in electrophilic addition, the electrophile adds to the alkene such that the most stable carbocation is formed. This is going to be our guiding principle for all electrophilic addition reactions, even ones that don't technically form a carbocation. We're going to see one of those in the third reaction we look at today. But this is going to be our guiding principle, that in electrophilic addition, the electrophile adds to the alkene such that the most stable carbocation is formed. This rule is so important that the chemist who figured this principle out has the rule named after him, and this is known as Markovnikov's rule. And so we'll see that Markovnikov's rule is going to control where different species react during electrophilic addition. So, since this is now what we formed, we know that our nucleophile will come along, attach to that carbon, and the overall process will give us a molecule that looks like this. Right? Again, our electrophile has added to the alkene such that the most stable carbocation was formed. So that's going to be our beginning guiding principles. I'm going to go ahead and move in now to looking at the first of the three reactions, addition of hydrogen halides to an electrophilic addition of hydrogen halides to an alkene, right? And we'll move forward from there and see how we can begin to apply our electrophilic addition principles to the formation of new reactions. So the first reaction that we're going to look at is addition of HX to an alkene, where here X is going to either be bromine or chlorine or iodine. So again, I'm going to start off with a unsymmetrical alkene. So that we can observe Markovnikov's rule in play for this reaction. And I'm going to just use HX, since any of these three hydrogen halides will work just fine for us. So we have hydrogen X, and since we're going to be doing an arrow pushing mechanism, we're going to want to have all of our electrons there. So as we've seen, in our first step, our alkene will act as a weak base. It's going to go ahead and grab the proton from our hydrogen halide. We know that this is an equilibrium process, and even though the equilibrium is unfavorable, it still occurs to give us our most stable carbocation, Markovnikov's rule. We have simultaneously generated X minus, which can now, in a second step, react with that carbocation to give our final product, an alkyl halide. Okay, so again we see here we have obeyed Markovnikov's rule. The electrophile adds to the alkene such that the most stable carbocation is formed. Our nucleophile then adds to our carbocation, and that's going to be the overall transformation that we see for addition of HX to an alkene. The next reaction, right, is related, except this time I'm going to do this addition in the presence of some sort of protic solvent that can either be water or an alcohol, right? So now we're going to go ahead and add, excuse me, I'm just going to add water across the double bond, skipping ahead to a future video lecture. So here now, our next one is going to be addition of H2O to our carbon-carbon double bond. So again, we're going to start with the same alkene. We'll have a unsubstituted side and a di-substituted side. So what we see here now for this example is that if we want to add water across this, well, water is not a strong enough acid for a weak base to be protonated, right? So we need a stronger acid than water. So what we do is we add into this reaction a really strong acid. We take water plus sulfuric acid and now water will pick up the proton from sulfuric acid. It's going to form H3O plus. H3O plus will serve as the proton source for the alkene to be protonated. Again, this is an equilibrium process which is disfavored, but still occurs. We will once again generate our carbocation, our most stable carbocation, following Markovnikov's rule. So we have now our tertiary carbocation, and we have now regenerated water, which will serve as our nucleophile, forming a bond to that carbocation. Giving us an oxonium intermediate another molecule of water can come along to serve as a base, deprotonating that oxonium. That's going to give us our product alcohol. And regenerating H3O plus so that this new molecule of H3O plus can come back to the start and repeat this cycle. What this means, since we're generating H3O plus at the end of every reaction, is we only need a very, very small amount of sulfuric acid to do this. In fact, we say that we only use a catalytic amount of sulfuric acid. In theory, all I need is literally one molecule of sulfuric acid, and I can do this reaction on a mole of our alkene, right? We use a catalytic amount of that sulfuric acid because all its purpose is to generate our first molecule of H3O plus, and then the solvent, water, does the rest of the job. It gets regenerated as H3O plus, which comes back, starts the process, and I never need to involve sulfuric acid in this again. So there is our second reaction, addition of water across this carbon-carbon double bond. Now, if you'll notice, this process, the use of H2O and H2SO4 to do this, produces for me a carbocation. And because I'm producing a carbocation, I have to be on the lookout for a carbocation rearrangement. Say, for example, I may produce a tertiary, but I might have the ability to rearrange that to form a benzylic or allylic, which would be resonance stabilized and more favorable. What if I want to do this addition without having to worry about carbocation rearrangements? We have another set of reagents that will allow us to do this without ever going through a carbocation rearrangement, and that's actually going to be our third and final reaction for this topic. So our third and final reaction for topic 19 is called oxymercuration demercuration, or more appropriately, oxymercuration reduction. This is what we're going to want to use if we want to add water across an alkene, but without generating a carbocation intermediate. So, our first step, right, we're going to have our alkene. And I'm going to use a unsymmetric alkene, right? But I'm not going to specify what the groups here are. Let's assume that it can potentially go through some carbocation rearrangement. The reagent we use to start this reaction is known as mercury acetate. So mercury, and it has 2 acetate groups on it. Now, the mercury has a charge of 2+. It actually has a very large expanded orbital set. The exact reasons it's able to do what you're going to see in this step are beyond the scope of this course. They're best left for inorganic chemistry or advanced synthesis. But suffice it to say that we have a simultaneous reaction between the mercury losing that acetate, so that the mercury actually forms a cyclic intermediate with this alkene, similar to a protonated epoxide that we've seen in the past. So that set of arrow pushing gives us this intermediate. So now we have a positively charged mercury making a 3-membered ring with my 2 alkene carbons, and we've lost this acetate group. And again, you should be able to see how this core structure, this 3-membered ring, where a hetero atom with a positive charge is very, very similar to our protonated epoxides that we've seen before. And they will behave in a very similar fashion, right? We can think that this tertiary carbon is better able to support a developing partial positive charge, which means that our nucleophile will preferentially react with the more substituted carbon. Again, this is going to follow Markov-Nikov's rule in that the nucleophile ends up on the more substituted carbon, or on where that most stable carbocation would be, right? And so here now we can use any sort of alcohol or water which goes ahead and opens up that ring for us, which takes us to this oxonium type intermediate. At this point, right, our acetate that we lost in our first step comes along to deprotonate our oxonium. We form an ether now. So here now we've formed an ether, and the final step, we use a special reagent called sodium borohydride, NaBH4, which is a reducing agent, and that reducing agent actually removes the mercury and replaces it with a hydrogen. The exact arrow pushing mechanism for this step is so far beyond the scope of organic chemistry that I will not expect you to know it. You should be able to push arrows up to this point, and then for the final step of the mechanism, just put NaBH4 over the arrow and draw your final product. And again, we can see that we've added a hydrogen and a nucleophile. We've added an electrophile and a nucleophile such that the addition of the electrophile by itself would have resulted in the most stable carbocation. So again, we have obeyed Markovnikov's rule, and we get the product that we want. But since we don't ever go through a carbocation, no rearrangements are possible in this reaction. So I'm going to clear this off and just do a quick summary of the 3 reactions that we've seen in this topic. Okay, so in this topic, topic 19, electrophilic addition, we've seen 3 reactions. We've seen adding HX across an alkene, and I'm going to use unsubstituted alkenes for this. Here now, I'm not going to do full arrow pushing. I'm just going to show the final products. So here we have added X to our more substituted carbon, and we've added the H to our less substituted carbon, i.e. we have added such that the most stable carbocation would form, right? The next reaction we saw was adding H2O, and I'm going to add in one little extra piece of information here, in that I don't have to use water for this reaction. I can add either water or an alcohol. So I'm going to put here ROH or H2O in the presence of sulfuric acid. And what that gives me, if I use ROH, that'll make an ether. Or if I use water, that'll make an alcohol. And because this goes through a carbocation, we know that for both of these reactions, rearrangements are possible. Now, the final reaction we saw was the oxymercuration reduction reaction. And in that, again, we begin with an alkene. We're going to use mercury 2 acetate, which can be abbreviated HGOAC2. And we can use either an alcohol, either an alcohol or water. If we use an alcohol, we will end up with an ether. Or if we use water, we'll end up with an alcohol. Again, this addition follows Markovnikov's rule, right? Overall, our final products are Markovnikov products, but because there's no carbocation, there is no rearrangement. No rearrangement is possible for our oxymercuration reduction. So this reagents first, and then, sorry to forget that, have to have sodium borohydride at the end. So 1 mercury acetate and an alcohol or water, and then finally, after that's complete, we add in sodium borohydride to get that mercury off of our carbon atom. Okay, so that's our first foray into electrophilic addition reactions, and this is going to wrap up topic 19. As always, thank you for watching, and if you have any questions, please feel free to bring them to lecture, conference, office hours, or make an appointment. Thank you very much.